Good afternoon. We are looking at the second lesson in our exponential functions and exponential and logarithmic functions. What I would like you to do now is to pause the video and use your graphing calculator, sketch y is equal, or f of x is equal to 2x, or y is equal to 2 to the power of x. Sketch it on the grid. Determine how would you describe its shape to someone. Determine domain, range, x-intercept, y-intercept, and horizontal asymptote. I then want you to do the exact same thing for g of x is equal to 1/2 to the power of x. And I want you to do the exact same thing. I'll keep up. Pause now and come back once you've finished that. Okay. So when you paused and went back to do this, you should have got the graph for y is equal to 2 to the power of x. You get a graph that looks like this. So I see a shape here, a shape that I'm seeing, and basically I'm seeing a graph that is rising as you go from your left side to your right side. Now, if I was to zoom out from this graph, you would see the exact same thing. Out. The graph's going to look exactly the same, but on a bigger scale. Okay, so we see rising from x left to right. We see that this is getting really steep. We're not even at 10, and we're up at whatever that number is there. Exponential functions get very steep very quickly. So what we have here for a shape of the graph is rising from left to right. We have a domain. Well, that graph's hard to tell on the domain, but it looked like it was continuing on all the way to the right here, or to the left here. And I guess I could check to see if it continues all the way to the left. It doesn't ever look like it's stopping. And if you were to trace, there's no gaps anywhere in this graph. So what we have here for a domain of this exponential function is all real values, which I'll write as negative infinity to infinity. Now the range definitely has a limitation. We have no values falling below the x-axis. So we have a graph here that is going to be y is greater than 0, or y is greater than or equal to 0. And one way to check to see, I'm going to trace to the left, so let's go trace. And I'm out there. I don't know what this is going to do. Get rid of it for a moment. Move. Negative 13. I keep going, and that's at negative 40. If I keep going out to the left, we're getting closer and closer to 0. Never going to get there. And again, this is a bit of a limitation. How do we know we're never going to get there? Because we cannot raise a number to an exponent to get 0 out. 2 to the power of negative 1 million is still 1 over 2 to the power of 1 million. It's very, very close to 0, but it isn't 0. Same thing if I go 2 to the power of negative 1 billion. Still 1 over 2 to the power of billion. We are never going to end up at 0. So our range in this case is 0 to infinity, exclusive of 0. There's no x-intercept. The graph is never going to hit y is equal to 0. So there is no x-intercept. The y-intercept, on the other hand, you trace 0, our y-intercept is at 0, 1. Now remember, this should make sense to us. Any number 2 to the power of 0 is 1. 65,235 to the power of 0 is 1. Any number raised to the power of 0 is equal to 1. So that's going to help us with this. So we have a y-intercept at the point 0, 1. And our horizontal asymptote, we can see as we go to the left, our number gets closer and closer to 0. You're going to have to kind of take my word for it. I'm not going to prove it to you. Well, I kind of have talked about it, proving it to you. It's never going to actually reach 0, so our horizontal asymptote has an equation of y is equal to 0. Now, if I go ahead and graph the next guy, my graph looks an awful lot the same, but it's flipped. Okay. We now, our shape of our graph is falling from left to right. Also decreasing. And so exponential decay is one of the ways that if we have a graph that looks like this, we have an exponential decay. Our domain is the same. Our range is the same. Our x-intercept is the same. 1/2 to the power of 0 is still 1. So our y-intercept the same. Try that again. Our x-intercept doesn't happen because we have a horizontal asymptote at y is equal to 0. And we have a y-intercept at 0, 1. Now our exponential graphs come in one of two flavors. A exponential decay function, like I've got here, where you fall from left to right, or an exponential growth function, where you rise from left to right. Now, these two graphs that we just put up here are horizontal reflections of each other. How are they horizontal? They look exactly the same. How do we know they're horizontal reflections of each other? Well, if I'm going to start with this one, 1/2 to the power of x. I can write 1/2 as 2 to the power of -1. So when I compare this to our original function y is equal to 2x, I've replaced the x with a negative x. Going back to our transformations unit, that is your definition of a horizontal reflection. We flip this graph around the line y is for x is equal to 0, or the y-axis. So, as I just said, we have a graph that's increasing. This is called exponential growth. Where you have your base value being bigger than 1. And we have an exponential decay function, decreasing, but also, as I said, called exponential decay, where the graph is between 0 and 1. Not equal to 0, not equal to 1. When you have 1 to the power of x, what do you get? You get a straight line. 1 raised to any power is 1. If you have 0 raised to any power except 0, it's going to be 0. 0 to the power of 0 is undefined. Basically, that's what we have. And those two things that we just did here, the domain and range, all of these are going to be the same for any untranslated, i.e. we haven't picked up and moved the graphs, any untranslated exponential function. Those are the things that will stay the same. So 10 to the power of x, 332 to the power of x, they're always going to be the same. Okay? So the domain going back to my shorthand, set builder notation is always going to be all real numbers for both. The range will be y is greater than 0, not greater than or equal to. This is the only thing that's changing. When your c is greater than 1, it's a growth function. When it's less than 1, it's a decay function. They both don't have horizontal asymptotes. Sorry, they both don't have x-intercepts. I don't know where that came from. They do have y-intercepts at the point 0, 1. And the equation of the horizontal asymptote in this case is y 0, i.e. the x-axis. Again, that is, no matter what the base is, with the exception, c can never be less than 0. C cannot be equal to 0. And c cannot be equal to 1. Let's talk about c cannot be equal to 1. You said that. 1 to any power is 1. So if you have 1 to the power of x, what you get is a straight line. That's all you get. Because any number, 1 to any power is 1. 0 to the power of x is equal to 0, or with the exception of 0 to 0. Okay. Now, what about negatives? Why can't c be less than 0? So let's just think about what we have. If we have y is equal to negative 2 to the power of x. Let's just do a table of values for this. We'll start at 0. So if x is equal to 0, y is going to be equal to 1. If x is equal to 1, y will be equal to negative 2. X is 2, y is going to be 4. X is 3, y will be negative 8. So we're going to be here, and then here, here, here. It doesn't work. Okay? Fraction. We can't have 1.5. Not defined. Because that's the square root, or we could write out it would be negative 2 to the power of 3/5, 3 over 2. Well, there's a square root in there. So there's places where it doesn't exist. So this is not an exponential function. It's not a function. We'll never talk about that. This is different, though, than that. Okay, how is it different? Well, it's going to do 2 to the x first and then multiply it by negative 1. So this is a function, and I can tell you my shape's going to look like that, because all I did was I applied a vertical flip to it. So it is possible to have the negative, but the difference is here the base is negative 2. The base over there is 2. We're just multiplying it by a negative 1. Here we have 2 untransformed. They're going to be in the form y is equal to c to the x. These two are. What's the equation of that? What's the base? How do we figure this out? Well, pick a point. Well, this point, don't pick this point, because this point's the same on everybody. That's 0, 1. Pick any point. I'm going to pick this point. I don't know why. I'm being difficult on myself. So that is 2. And if I go over here, a little higher. Graph should be 16. Yes. Okay. So I'm just going to say, I know y is equal to 16, c is equal to some number, and x is equal to 2. And read that off our graph. So, okay, we have not an exponential function, just a normal function. I'm going to take the square root of both sides. So c is equal to plus or minus 4. we know c cannot equal to minus 4 by definition, so c is equal to 4. Any point on that graph would have given you the same thing. I'll pick this one here, -1 and 2.5. You probably guessed that my base is going to be either fractional or have a negative exponent. I'm going to solve my fractional one here. So 2.5 is equal to c to the power of -1. Raise both sides to the power of -1. And I have 1 over 2.5 is equal to c. I do not like 1 over 2.5. If you want to write that as a decimal, that would be perfectly fine. I'm going to write this as 2/5. If you want to write it as 0.4, that's fine too. All I did was I multiplied both the numerator and the denominator by 2. So I have I have y is equal to 2/5 x. Now I could write this as 5 over 2 to the power of -x. Both would be acceptable. Probably not going to come out of that very easily. I would solve to the 2/5 to the power of x. So again, what I suggest is you take a couple gander at these questions here, go through them, see if you can do them. I will be going over them tomorrow. I shall see you in class. Have a good afternoon.